Okay, so last time we started to study Batalin-Vilkovisky formalism, and we introduced a notion of a BV system, not a very general one, but the one which we arrived at starting from BFV formulation of a first-class constraint system. And the last thing we discussed was a typical example. It's a little bit of a toy model where we have a field anti-field space containing variables phi I of degree 0 and variables C alpha of degree 1. So here 0, here 1, plus their conjugate anti-fields psi star I and C star alpha. Of course, these guys are of degree -1 and -2 respectively, so that the anti-bracket has degree 1 as it should. So let me remind you that we postulate the standard choice for canonical anti-bracket relations. It's pretty much similar to Poisson bracket, except that momenta has different degree and Grassmann parity. So this is delta ij and C alpha C star beta is delta alpha beta, right? So this is our field anti-field space. Degrees are like this. And we want to study this simple system to understand the structure of the master action, the structure of BV formulation. Here there is an important subtlety which we need to discuss a little bit. So as you can see, now I pretend that I have finite dimensional space with coordinates phi C, phi star, C star, right? But realistically, if we want to describe field theoretical or even mechanical system, we always have our space of field configurations is infinite dimensional, even in mechanics, because space of possible trajectories of our mechanical system is infinite dimensional. And the situation becomes even worse in the case of field theory. So when we play this game, when we say that we consider a BV system, and we do not, and we work with it as if the field anti-field space were finite dimensional, strictly speaking, we are describing something unphysical, because even mechanical system is not like this. So there are two interpretations. Interpretation one, that we are just playing a game, so it's a toy model, which doesn't have a direct relation to realistic mechanical or field theoretical systems. And second interpretation is that actually the space is infinite dimensional. We think of our index, for instance, I, as condensed, what's called condensed index or condensed notation. So it contains a genuine index, finite index numbering our fields, and coordinates, the continuous part of our index, coordinates x mu on the underlying space-time, which means that, for instance, if we consider a summation over such an index, for instance, if we consider AI BI, this expression realistically means that there is an integral ddx, then there is a let this index be capital, like this, ai of x, bi of x, right? That's what's called condensed notations. Often to grasp very general properties of the formulation, it's very useful because you don't need to write explicitly integrals. You can really think in naive geometrical terms. Everything is fine, but of course you lose in this interpretation, you lose many important subtleties related to field theoretical nature of our system. For instance, the first thing which you immediately lose is locality, manifest locality rather. Still can be perfectly local. Manifest locality. Because for instance, if I write generic matrix Aij, it can perfectly be non-local because it can depend on point X here and on point Y here. And usually in field theory, we prefer not to consider generic objects of this type. And often we even restrict ourselves to so-called local objects, local functionals, etc. Not always. Sometimes we need a slightly non-local objects like, I don't know, Wilson lines or things like this, but these are very special and their non-locality is quite under control. So this is a very important remark. Unfortunately, things are not so simple. This also explains why it is very pedagogical to first study Hamiltonian formalism, because you can understand physics at the example of a finite dimensional system, and still this finite dimensional system has direct physical interpretation. At least in mechanics, our Hamiltonian formulation is usually finite dimensional. But this is not the case if we are working with Lagrangian formalism and in Batalin-Minkowski formalism in particular, because it's like an extension of Lagrangian formalism. Because even mechanical system has an infinite dimensional underlying infinite dimensional space, in our case, field anti-field space. Okay, so this is an important remark. We will get back, if we have time, to the discussion of locality in some more details later. But for the moment, we really disregard these subtleties. We just want to understand the very basic structures of this BV formalism. And in simple cases, if it is needed, we can just explicitly think of our indices as a combination of like discrete index and the continuous index, which parameterize our points of our space-time. Okay, and this was an exercise from last lecture that we can consider generic mass direction. I decided not to write BV because it's not very economical. So I just use S. Well, so before I tried systematically to put BV, now S without anything would mean BV action, while classical action is the one with not, the one we start with. So now we consider generic function of these coordinates, which has degree 0 as mass direction should. So the expansion in variables of non-vanishing degree looks like this. So first we have with something depending only on degree 0 variables. Then we have in general something like this, phi star I Ri alpha, phi C alpha. And then we have phasor terms, but let me write two of them, which contain variables of. So at this point, it's also convenient to introduce resolution degree, right? So resolution degree of phi star I is -1, and resolution degree of C star alpha is -2. And the remaining variables, they have vanishing resolution degree. So this term has resolution degree 0. This term has resolution degree -1. The next term is going to have resolution degree -2. There are two possible terms like this. So one is usually written like this: C star alpha U alpha beta gamma C. Sorry, round. Gamma alpha beta C alpha C beta, and there is also a possibility of the term of the following structure: Mij alpha beta. Here we can put phi star I, phi star j, C alpha C beta, and this has resolution degree -2 because of so this is -2, and this is also -2 because -2 we can form in two ways: either linear in C star or quadratic in phi star, plus higher order, higher resolution degree terms. Resolution degree greater than 2. Well, resolution degree we count with plus, so it should be +1, +2, etc. Okay, that's what the expansion looks like. And that was an exercise. The exercise was to analyze the master equation. Which kind of equations it gives to these functions S0, Ri alpha, Um, which enter the expansion of our mass direction with respect to antifields and ghosts. And this expansion is fixed by also, so this is expansion in resolution degree, but also the structure of the term is fixed by the requirement that ghost degree of our S is 0. So for instance, if we have phi star I, which has degree -1, ghost degree -1, it should be compensated by something which is C alpha. This is the only variable which has degree +1, ghost degree +1. So that's why the structure is like this. Okay, I hope you considered this exercise and you found that we get the following consequences of the master equation. So we just write S equals 0, and C terms which enter, which contain these lowest order terms in resolution degree which we introduce, and see what it gives. So what it gives, it's easy. It's actually a simple exercise. Is that ds0 over d d phi I times Ri alpha 0. This is what we get in degree 0. And then the next equality reads like this. It's if you think of R as vector fields in phi space, then the commutator of I component of the commutator of R alpha or beta equals to beta gamma R I gamma plus Mij alpha beta d phi j. Yeah, that's what it looks like. I'm not careful with, so let me put something here. I'm not sure about coefficients. This depends on definitions, and anyway, it was an exercise to check it. And then the further equations which we infer from our master equation, they already start to involve higher order structures. So in addition to this R and U, you get, and S0, you get higher coefficients, and they are not so interesting, and we will see why. It's the same story like in the Hamiltonian case, where only the beginning of the expansion of the Beresty charge with respect to ghosts is interesting, because the rest always exists under regularity conditions, and the ambiguity in it is described But what is important is to fix these very first terms because they contain interesting information about our gauge system. Okay, so what is the meaning of this equation? So this first equation is kind of clear. This is a very important equation. It's called Noether identity. Or you can think of it differently. You can think of it as a condition that action S0 is invariant under gauge transformation with the gauge generator Ri alpha. So there are two interpretations. Interpretation one is that this ds not over d phi I, let's denote them as ei. These are of course nothing but Euler-Lagrange equations for. If you really take field theory, then these are going to be Euler-Lagrange equations of motion determined by action S0, right? So what's written here is that Ri alpha, so what is here, is that Ri alpha are like determined linear dependencies between equations of motion, between EI, right? So our EI are not linearly independent. They are dependent. And dependence between equations of motion is called Noether. These identities which express it are called Noether identities. Another interpretation of the same formula is that our action is invariant under gauge transformations. So this is interpretation one. Interpretation two, S0 is invariant under the following gauge transformation: delta phi I equals to Ri alpha epsilon alpha, where epsilon is a parameter. Remember that if we are talking about field theory, then epsilon alpha is actually, because it's completely general, it's a generic function of space-time. So this is really gauge transformation. In case if you're talking about toy model, we still call it gauge transformation, but we understand that in this interpretation is kind of limited because there is no real physical system underlying it. It's like field theory in 0 dimensions, if you want. Okay. It's clear, right, that if we perform such a transformation of phi with generic parameter epsilon alpha, our action is invariant thanks to this equation. So there are two interpretations of this equation, either as a identity reducibility relation between equations of motion, so equations of motion are not independent, or as a condition that our action is invariant under gauge symmetry. When we switch to field theory, these two interpretations become not so similar because one has to be a bit careful with because it's not any longer ds over d phi, but it's like variational derivative or Lagrange derivative. We will consider this, but for the moment we disregard these subtleties. We really work just with the finite dimensional field antifield space. Okay, then let's get to our second equation, this one. What does it tell us? It tells us that so these R's are generators of gauge symmetry. So it is natural that a commutator of two gauge transformation is again a gauge transformation, and that's what exactly this equation tells us, right? We take a commutator of R alpha with R beta, and again we get something which is proportional to a gauge generator, which means that we again get a gauge transformation, but there is an additional term, this term with M. And this term is very strange. It also contains S naught. Any idea what is the meaning of this term? At first glance, sorry, yep, I'm listening.
Interaction.
Well, not really, not necessarily. Well, it's difficult to find such a term in free theory, in linear theory, indeed. But strictly speaking, it's not directly related to interactions. But you see, it's something very strange that you would expect that commutator of two gauge symmetries is again a gauge symmetry. But here you see that it is a gauge symmetry, but up to a term, up to something. So strictly speaking, we commute to gauge symmetries and we get something which is not a gauge symmetry. And in fact, the answer is that what we encountered is a notion of trivial gauge symmetry. Which has nothing to do, which is always present, and which has nothing to do with real properties of our system. So what is trivial gauge symmetry? It's a symmetry of the following form. Delta phi I equals to mij ds naught over d phi j, and this matrix is, which can be perfectly a function of phi, but what is important is that it is antisymmetric in indices ij. And recall that our mij here in our equation is antisymmetric. Why? Because it enters, you see this in the expression of our master action. Here it enters, its indices are contracted with phi star, which is our simplified setup, are fermionic variables. So if we exchange them, we get minus sign. So we can assume that this mij is antisymmetric. Anyway, its antisymmetric part enters, so it should be antisymmetric. So, and this is a trivial gauge symmetry, right? Because if we now consider, if we now consider delta S naught, so let's call it delta t. Delta t is naught, it is identically zero. Why? Because when we apply, we get what? We get ds naught over d phi I, and then we get mij ds naught over d phi j. But because our matrix is antisymmetric, and it is multiplied by, and these objects are bosonic, so they're commuting, so we get identically zero, right? So given whatever action, we always have a gauge symmetry. Parameterized by generic antisymmetric matrix. But this gauge symmetry is not very interesting. Why it is not very interesting? Because its generator, look here, its generator is proportional to equations of motion. So this transformation vanishes on shell, on the surface of solutions of our equations of motion. By the way, let me write it here. So sigma, which is like collection of points where ds naught over d phi I 0 is called stationary surface. Stationary surface. Because it's a surface where our action is stationary, right? So the term is clear. Also in the literature, it's often called shell. That's why we say on shell or off shell if we are sitting on this surface or off this surface. That's traditional terminology. Okay, so what is important? These trivial gauge transformations, they vanish on sigma, which means that if we really want to see how our physical configurations are transformed under symmetry transformation. We take a solution to our equations of motion. In our toy model, this means a point where ds over d phi is 0, ds not over d phi is 0, so a point of sigma. And we see how our transformation act on this point. And we see that because generator vanish on sigma, it doesn't affect solutions. But physical states are actually solutions to our equations of motion, at least classically, right? So what happens off the stationary surface is not so important. And this formalism, which we are studying now, somehow knows this at very deep level, because you see, it tells us that if we pick a basis in the space of our gauge transformation, which means these vector fields are alpha, and if we commute them, we get again something proportional to R alpha, but up to trivial transformation, because this term here is just a particular trivial gauge transformation, right? So this means that our gauge algebra is a very vague term. In a sense, it's like infinite. Strictly speaking, gauge algebra is something like infinite dimensional algebra of all possible gauge transformations of our action. So this algebra contains this trivial gauge symmetries as well. And if we pick a particular basis, we get a closed algebra only modular trivial gauge transformation. This phenomena is called open gauge algebra. Again, terminology is very old and not really perfect in my opinion, but it's a matter of taste, because also term gauge algebra sometimes is referred in the context of Young-Mills type systems. Just, for instance, if you have Young-Mills with SU2 algebra, we call it gauge algebra, right? But it's different. This algebra is perfectly closed, and this has nothing to do with this phenomena. For instance, this kind of theories appear in there are some supergravity models which are theories with open algebra, and some other more related to gravity. But in principle, we can take a very simple gauge system and just choose a wrong or not convenient set of these gauge generators R, and we can end up with open algebra. So what's a good point is that our formalism knows about this possibility and seem to control it. Okay, very good. So this we understood the meaning of these two equations. So first equation, which is contained in the master equation, is precisely the condition that our action S0 is invariant with respect to gauge symmetry generated by R. And second condition tells us that gauge generators R form in general an open algebra, which means that gauge transformation close on shell. So if we commute two different gauge transformations, at least for points of the stationary surface, a commutator is again a gauge transformation. Okay, very good. It's time for an example. It's a very simple one, where of course we are not going to have all these tricky situations. Let's take just maximum. So our S0 is something like d4x f mu, right? F mu is as usual d mu a nu minus d nu a mu. We're in four-dimensional Minkowski space, and we know what gauge transformations are. We know that delta a mu is, put epsilon here, is d mu epsilon, and this is a symmetry of this action, right? So it's not difficult to write down BV action. So we know that ghosts somehow should be associated to gauge parameters. These are like gauge parameters, but with shifted degree. So we introduced ghost C of x. They're just scalar fields in some sense. Well, of course they're not scalar fields in a physical sense, but in the sense that it's a fermionic field which is scalar with respect to Lorentz group. Okay, and then we need to introduce our antifields, I star mu, and we need C star. This is in degree -1, this is in degree -2. And it's easy to write down BV action in this case, just to guess, there is nothing, it's S naught plus integral d for x A star mu d mu C. And if you it's an exercise, very simple exercise to check it, that SS is 0. So, and in fact, checking this precisely amounts to gauge invariance, because when we compute a bracket between this term, and this is the only possibly non-vanishing contribution, right? Because S naught depends on only on our gauge field A. So S naught with S naught is 0, of course, because there are no antifields. Then we compute a bracket between S naught and this term, and we see that the possible contribution comes from A star, because A star is like odd momenta for A. So what happens, it precisely looks like gauge transformation, right? ds naught over dA. So what you get integral d for x ds naught over dA mu of x, and then you get d mu c, right? And this is 0. Because S naught is gauge invariant. Because S naught is a function of f, so if you compute it, you get 0. It's just another way of writing gauge invariance. And all these other structure coefficients of the master action can be taken trivial in this case, so further conditions are not needed. So that's a very simple example. Okay, very good. So then we discuss what's called, it's more or less the same story like in Hamiltonian case, that in BV case we can also define BRST differential. So it's a traditional name notation for it is S, small s, and this is result of taking, it's a Hamiltonian vector field in the sense of this odd bracket or anti-bracket, whose Hamiltonian is the BV action. So S squares to 0 thanks to master equation. Again, to check it, we need to use Jacobi identity. So if we do it twice, for instance, if you want S squared on F, what we write? We write S SF, right? Then we use Jacobi to get SSF, right? And then we get one more term minus SSF, right? Here it is just Jacobi identity. So what we see that this term is exactly the same but with opposite sign. So if you just concentrate on this identity, we can take this to the left, and we will see that twice this term equals this, but this is master equation, so this is 0. So it's exactly the same argument like in like we considered more carefully in the case of Hamiltonian, systems, right? And we prove that this is 0 then. So you see, master equation implies that the Hamiltonian vector field generated by master action is nilpotent. So again, we get a complex, a BRST complex, BV, but BV maybe. BRST complex, so which is our functions on our field anti-field space together with a differential S and degree GOST, because GOST degree of S equals 1. And our algebra of functions of fields and anti-fields is a graded algebra with the degree being GOST number. So S rises this degree by 1, so we get a perfect homological complex. Sometimes it's called BV-BRST complex, but again, the problem is things become not so simple compared to Hamiltonian setup, because again, because we are talking about toy model. So if it's a toy model, we can call whatever. If it's this space M is finite dimensional, then this is a perfect complex. It describes something, but this doesn't have much to do with physics, right? But if you want to construct this object and in such a way that it has meaning for a field theory or just mechanics, then one has to be very careful, because this space M is infinite dimensional. And when I write this, means like functions on infinite dimensional space, this is something huge, and you need to say which kind of functions, how to define them. In fact, this M is like a space of configurations of fields plus all these GOSTs and anti-fields, what are boundary conditions, all these issues come into the game immediately. So this object is useless. You really need to say more and more to give it a meaning. And of course you can proceed formally, but then you are not expecting to get something meaningful. And realistically, what happens in field theory, for instance, to get a meaningful cohomological theory, you need to take, for instance, so-called local functions instead of functions on M. Well, functions on infinite dimensional space are functionals, right? Functionals, local functionals. And already in this space, cohomology becomes meaningful and they have direct physical meaning, but this requires more sophisticated techniques. So for the moment, our considerations are quite formal, though still this differential can be given some meaning. Nevertheless, at least we can understand conceptually how it works. Okay, and given this, so we disregard these subtleties. Somehow we assume that everything is prepared properly and we work in a correct functional space, like local functionals or something like this, so that it has a meaning. But for the moment, we don't discuss these subtleties. So what we want to do, we want to play the same game as we did when we studied Hamiltonian systems. So we studied the structure of this differential in some more details, and this allowed us to prove statements like existence of solution to the master equation. We were able to describe ambiguity in solutions to the master equation, etc. In fact, at algebraic level, and if we disregard the subtleties related to infinite dimensionality, the picture here is completely analogous. So we know already everything. We just need to understand how to identify objects. And that's what we are going to do now. So we are going to repeat the story of which we already studied in the case of BFV formulation. We want to repeat this story here and get some useful statements. And if you remember, the important ingredient in that case was the resolution degree. Now, it can be introduced in general setup. So, for instance, R degree of a coordinate function psi a is 0 if ghost of psi a is non-negative and is minus ghost of psi a in the case if ghost of psi a is negative. So this is a way to introduce resolution degree without referring to a particular structure of fields and antifields. And then we expand our S in terms of resolution degree. And again, we call the lowest term, which happens in degree -1. You can count degree and check that it must be like this. And then we just get expansion with respect to, so this is 0, this is 1, with respect to resolution degree, so that the resolution degree of Si is I, and resolution degree of delta is -1. And in fact, this delta is almost the same object as we had in case of BFE formulation. So delta is a kind of Koszultay differential. In particular, delta squares to 0. On account of, because S squares to 0, so its lowest degree term must also square to 0. Then, of course, we have, in addition to this, we have that delta commutes with S naught in the sense of graded commutator. And we also get something like this, that S naught squared plus commutator of delta with S1 is 0, right? And some further consequences of, so we just study what nilpotency of S tells us about algebraic relations between this delta S naught and S1. I'm speaking about this expansion. So in particular, we see that delta is nilpotent and S naught commutes with delta. So let's look in some more details what delta is. For example, in our simplest model, simplest non-trivial model, where we have phi star, C alpha, and C star alpha, our delta reads like this. It's ds naught over d phi I plus this phi star I ri alpha d over dc star alpha. It's a simple exercise to check that only these terms enter. So it pretty much look like Koszultay differential. Indeed, let me remind you that when we consider first-class systems, we had our delta, let's say delta B of V now, looked like this. It was T alpha d over d pi alpha plus, if there are relations, pi alpha z alpha a d over d rho a. That's what it looked like. Exactly the same structure. And the identification is obvious. So, oh, sorry, here there is a typo. I have to correct it. It's phi I d over d phi star I. Yeah, now it's okay. Yes, so you see, it's one-to-one. So what is identification? We can even write some kind of table. So here we have BFV, and here we have BV. So you see that the first term, here we have equations of motion, and here we have constraints. So from the point of view, from the purely algebraic point of view, it's exactly the same, but now constraints T alpha correspond to, they are just replaced in, they are just replaced with Euler-Lagrange equations. Euler-Lagrange equations, which are ds naught over d phi I, right? In particular, constraint surface sigma is replaced with stationary surface sigma, right? Here we have variables phi star I, c star alpha. Here we have variables pi alpha rho a. Of course, indices runs through different values, so this alpha should not be really identified. Okay, so we see that the Koszul-Tate differential look exactly the same, and of course the job it does, its job is to describe the restriction to the constraint surface in the implicit terms, in homological terms. So in the case of BFV, we knew that what our Koszul-Tate differential gave us a resolution of the algebra of functions on the constraint surface. Now this BV differential now does the job of its cogomology is algebra of functions on the stationary surface. So everything is identical. The only subtlety is that the role of variables is very strange, right? So now our variable c star alpha correspond to identities between our equations of motion, right? Before, in Hamiltonian setup, we had these variables rho a, which were responsible for these relations between constraints. Now our constraints are equations of motion. And if our theory is a gauge theory, there are noether identities between them, and these noether identities, they are determined by gauge generators. You see, so gauge generators play a role of reducibility relations between Euler-Lagrange equations. That's how things look differently, but interpretation is different, but algebraically the situation is exactly the same. And then we can write down also, we can consider S naught, the 0 resolution degree term in our Beresty differential. And now it looks like this. It looks like C alpha Ri alpha d phi I plus minus, be careful, I can't remember all possible correct signs, so it has to be checked if you want them to be really correct with the given conventions. So here we get C alpha C beta U alpha beta gamma do dc gamma plus antifield dependent term. Dependent in general, dependent terms. And again, this in case of so S naught is actually identical. Even our notations are such that S naught look exactly the same in in the case of BV and BFE. Of course, the meaning is slightly different, right? But what is the same in both cases is that variables C alpha are ghost variables and R are gauge generators. And the formula for S naught is the same modulo these antifield dependent terms, because they don't have analog in the Hamiltonian picture, right? But what exactly formally coincide, because notations are like this, is the differential gamma, which is, if you remember correctly, which is by definition S naught restricted here to the surface T alpha equal to pi alpha equals 0. And here the analog of this is differential gamma, which is S naught restricted to the surface, stationary surface. So this is 0, and also well, here we also, by the way, we also need to put to 0 the raw variables. And here we put to 0 this and antifields variables. Yes. So one can check that S naught is tangent to such a surface. We discussed this in case of BFE. The situation here in BV is algebraically analogous. So you can check that if we set antifields to 0 and set equations of motion, and require equations of motion to hold, so it means we set to 0 ds naught. S naught is tangent to this surface, and its restriction is denoted by gamma. So gamma, if you remember, we called it gauge differential, and it is given just by these two terms restricted to the surface. So it is identical. So now, in fact, we know many things through this identification. We can just remember which statements we proved when we discussed Hamiltonian setup, and just immediately recover their analogs in BV setup. So for instance, cogomology, first of all, we need, let's formulate it as a proposition. So suppose let Ri alpha be independent. In the literature, it's often called irreducible, which means that there are no non-trivial relations between R. Non-trivial means non-vanishing on the stationary surface. And Ri alpha exhaust relations between so these are all non-trivial relations between Euler-Lagrange equations of motion. So if these conditions are satisfied, we say that we talk about irreducible gauge system. So there are independent gauge generators, and there are no, they exhaust the gauge redundancy of our action, and there are no relations between them. Okay, then cogomology of Koszultai differential is given by functions on stationary surface tensored with polynomials in C alpha. And 0 otherwise. So this we proved already. We see that it's exactly the same operator. So if the same conditions are satisfied, which now have different physical meaning, then we have this statement. So Koszul-Tate differential resolves the algebra of functions on our constrained surface. Then we have the following corollaries, because we already proved everything. Mathematical statements, we know that cohomology in Gauss degree 0 of S is given by gauge invariant. Again, we are in finite dimensional case, otherwise the situation is much more difficult and requires additional technique which we have not yet studied. Gauge invariant functions on sigma, right? That's what we proved, because we know that we can actually compute cohomology of Koszul-Tate, and in cohomology we get this differential gamma. It's a quasi-isomorphic complex, and because gamma look like this, so in degree 0, if you just get that R on representative should be 0, so which means we are talking about gauge invariant functions. That's it, right? So we have this corollary. Then we have existence statement. So we can repeat the story about how we existence, and that we can prove that there exist S such that SS is 0, Gauss S is 0, and S equals to S naught plus phi star I alpha C alpha plus high degree terms. So it means that if we are given with the classical action S naught, and we have independent generators which exhaust the gauge, independent gauge generators R which exhaust gauge symmetries of S naught, this means that we can construct S, because the construction is purely algebraic, and the only step which is important is that delta doesn't have cohomology in positive resolution degree. So we expand S with respect to resolution degree, and we repeat the proof. Algebraically it is identical, so it's a good exercise. Give an explicit proof. And also we can formulate ambiguity. We can describe ambiguity in S in exactly the same way as we described ambiguity in the solution to master equation in the case of Hamiltonian formalism. So, and again, ambiguity is given by canonical. In this case, canonical in the sense of anti-bracket. Sometimes it's called anti-canonical, canonical transformations. Let me recall you what it means. It means that if we have two solutions to master equation, to this equation, such that the degree 0 and degree 1, resolution degree 0 and resolution degree 1 terms coincide, then there is a canonical transformation which takes one to another. So they are related by canonical transformations, and hence they describe same content. And again, it's an exercise to prove it. It's just literally step by step the same proof which we had in the Hamiltonian case. The only difference that now we need to use anti-bracket instead of Poisson bracket, of even Poisson bracket. Exercise, give a proof. It's a repetition, but some notations are different. It's but the content is the same. Okay, good. Now we need to proper master action. We need to discuss one important point. So suppose we want to use BV formalism to describe a theory with action S0 of phi. And suppose this action is gauge invariant. Then we can say, okay, very good. We know what to do. We should find gauge generators. So we know that we should build BV action, which looks like this. It's S0 plus phi star I alpha C alpha plus more. And we know that this more exists because if R exhaust gauge symmetries and independent, then you can find these additional terms in order to satisfy our master equation, right? So we construct a BV formulation, but at the same time, someone can say, fine, I don't want to work. I just take S to be equal to S0. I'm not going to introduce antifields. I'm not going to introduce ghost. I don't want to consider, let's say this is S prime. I don't want to look for these correction terms. So I just take S0 as my master action. It perfectly satisfies master equation just because there is no dependence on antifields. So everything is good. What's wrong? What's wrong with this action? Why? Well, it's kind of clear that it doesn't describe all details of our gauge system. But is there a way to somehow tell immediately that this S prime is not a good BV master action, which takes into account all necessary information about our gauge system? Any ideas? Okay. Can you hear me? Is everything fine?
Yes.
Okay. So the question, let me try to reformulate my question. So it looks like we need some additional condition to be imposed on our master action in order to be sure that it is a correct master action, that it really takes into account all gauge degeneracy. Because we know what happens if we identified all gauge symmetries, so which means we have a complete set of independent generators R, then this is the answer, right? And these correction terms are not so important. We know that we can recover them if all conditions are satisfied. So that's what we need. But how can we say that this is good BV action without digging into details where fields are, where anti-fields are? This is not so clear, right? But in fact, this is a condition. One can impose this condition, and traditionally it's called proper master action. It's a master action which satisfies this condition, proper master action. In fact, it's somehow maximally non-degenerate. So what is important is to look if we like, for instance, psi I, like all fields and anti-fields. Then what we need to look at is what's called Hessian matrix, d psi I, d psi j, and consider it on, we are only interested in points where equations of motion are satisfied, and we need to consider its rank. And in fact, it should be like dimension of our M by 2. It should be maximal. Of course, strictly speaking, in this form, this condition only applies to toy model, where everything is finite dimensional, because otherwise we don't know what dimension is. But the idea, it should be somehow maximally non-degenerate. This rank should be maximal. Let's see that this holds for our actually, this is an exercise. It's a good exercise. Check that this holds for our S equal to S naught plus phi star I R I alpha C alpha plus morph. In fact, it's very simple, right? Because if we consider the sector of this matrix associated to initial fields, so coming from here, right? So we will see precisely this Hessian matrix of our classical action S naught, which has certain zero modes, which are precisely these R. So if these R generators exhaust zero modes of S naught, this makes this matrix of maximal rank. And this rank is 1/2 of the total. Why 1/2? It's also very easy to see. Let's consider our differential. It's easy to see in terms of BLST differential, this one. So this S squares to 0. Let's consider it. Let's consider like this, Si of psi d over d psi I, right? Now I use psi I to denote all coordinates on my field anti-field space. So what do I see? Of course, this Si is nothing but ds or d psi j, eij, oh sorry, j e ji, yeah, like this, where E is a matrix of our anti-bracket. And then let's consider S equation S squares to 0. So what it amounts to? It amounts to Si dsj over d psi I equals 0. This is I have just rewritten this condition in coordinates, right? And then let me do it slightly differently. So let's Yeah, let me take d over d psi k of this identity of si dsj over d psi I, and after computing the derivative, let me restrict it to a point P such that it's a zero locus of S. So Si at P equals 0. So there are two terms here, right? So I just consider consequence of this. I take a derivative and evaluate it at a particular point. I know it must be 0. So there are two terms. So derivative with respect to psi k first hits Si and then this one. But the second term vanishes at P because it's proportional to S. So what we get is dsi over d psi k dsj over d psi I at point P is 0. So if we denote this matrix ds over d psi at point P by Q, then what it says that this matrix is nilpotent, right? Because it's matrix multiplied by itself and it is 0. But from this, it follows that rank nilpotent matrix can't have rank greater than half of the dimension, right? So it's maximally non-degenerate. So the best you can get is maximally non-degenerate as corresponds to the situation where this rank is precisely 1/2. But what this matrix Q is, this is precisely, let me remind you that Si is just first derivatives of master action multiplied by this matrix. But this matrix is invertible. You can think it's a constant invertible matrix in good coordinates. It's just some Kronecker deltas, right? Because it's our Poisson bracket matrix. So this means that our Q, that the rank of, so d over d psi k of Si is nothing but d at P is nothing but d squared of S d psi k d psi j e j I, right? So because this matrix is and this is at point P, because this matrix is invertible, it follows that our condition on rank and precisely on this Hessian matrix. So that's quite it's essentially purely algebraic considerations, which tell us that the rank of this matrix, like second derivatives of our BV action, can't exceed half of the dimension, and proper master action precisely corresponds to the situation where this rank is maximal. Unfortunately, again, all this is so simple if if we are talking about this toy model. If we are not talking about toy model, one has to be more careful, but the condition of properness tells us that all gauge invariances of our action are taken into account in our master action. If it is done, then our S is proper. In particular, a simple criteria of S, which holds in field theory, S is proper if the respective delta Koszul-Tate differential doesn't have cohomology. positive resolution degree in the space of local functions. You're not supposed to understand deeply this because for them we have not discussed how all this works really in field theory, but there is a proper space where Koszul-Tate differential of a proper master action should be good. It means that it should give a resolution of functions on stationary surface. But at the level of toy model, it's enough to require this rank condition. So it's very important that a genuine BV description means that we have our master action should be a proper master action, means satisfying some additional condition, which in finite dimension is just this rank condition. Okay, very good. Let me say a few words about, reducible. I'm afraid I don't really have much time to speak about this reducible gauge theories, but still we need to mention this. So the situation here is completely analogous to what we discussed in the Hamiltonian case, and this corresponds to the situation where you have your action S naught of phi. You have gauge generators, I alpha of, strictly speaking, phi. These are gauge generators. But they are not independent. The fact that they are gauge generators means that if we consider transformation of fields like delta epsilon of phi I equal to Ri alpha epsilon alpha, so if we consider such a transformation of fields, our action remains unchanged, right? This is precisely the ds naught over d phi I Ri alpha equals 0, right? For any epsilon. You see, we have this identity. If you multiply it by epsilon, this identity is precisely precisely tells us that our S naught is invariant under such a transformation, right? For any epsilon. Okay. But now, before, we assumed that R are independent. But now, independent means the following, that if there are relations between R, they vanish on stationary surface. But now suppose that there are non-trivial relations, that Ri alpha, there are some functions z alpha a, such that it is 0. This equality holds on shell. So this means modular terms vanishing on equations of motion. So ds naught over I times something. So this weak equality is also often used in the literature and called weak equality. So equality modular terms proportional to equations of motion. So if there are relations between our R, which themselves, the z on sigma is not 0, then we are talking about reducible gauge theory. And so, for instance, stage 1 reducible theory, or reducibility stage 1 reducible theory, is when there are non-trivial relations between gauge generators, but there are no relations between relations. So it means that if z alpha a, there are some functions, let's say z2 a mu, it follows that this Z2A mu vanish on the stationary surface. So if this holds, it means that we are talking about stage 1 reducible theory, where there are relations between gauge generators, but there are no further, like next stage relations. In principle, there can be few stages. There is nothing very non-trivial about this. There are examples of such theories, and this BV formalism perfectly captures this possibility. You just need to introduce further ghost variables and their associated antifields. For instance, in this case, for first stage reducible system, you introduce ghosts eta A and their antifields eta star A, and ghost degree of eta A is 2. So ghost degree tells which level of reducibility we are talking about. So there are ghosts of degree 1, they are associated to gauge generators, and ghosts of degree 2 are associated to reducibility relations between gauge generators. Another name of this, maybe let me, no, here I don't have space. Another name of this is gauge for gauge, for these reducibility relations, gauge for gauge symmetries. Indeed. So because we have Ri alpha Z alpha A equals 0, modular equations of motion, we know that our delta S naught is 0, right? Transformation of, of course, we know that our action is gauge invariant with respect to gauge generators R. Now we can introduce something like gauge transformation of a parameter. So our gauge transformation look like this: delta phi I Ri alpha epsilon alpha, where epsilon alpha is our gauge parameter. For whatever epsilon, this transformation of phi, strictly speaking, it's good to write epsilon here. For any epsilon, such a transformation is the symmetry of our action, right? But we can also consider a symmetry for acting on epsilon. We can say, okay, now I shift my epsilon, delta epsilon alpha, equal to, and that's where exactly this Z alpha A, lambda A, where lambda are now parameter of gauge for gauge symmetry. You see, and if we consider such a transformation of parameter, it turns out that, let's say, delta, let me write it like this, delta epsilon plus delta epsilon of phi I equals 0, but modular terms proportional to equations of motion, which means that if our phi is a solution, such a transformation what I wanted to say is this, epsilon of phi. So if we change in such a way our gauge parameter by a trivial transformation, the gauge transformation doesn't change in general up to terms proportional to equations of motion. It's obvious because, of course, if we write it down explicitly, delta epsilon plus delta epsilon, it's infinitesimal, so we just get a sum. So we get delta epsilon phi I plus transformation generated by this, which is Ri alpha, Z alpha A lambda A, and we know that this is 0, and this is delta epsilon phi I plus something, and this something vanishes on 0 because vanishes on stationary surface because this vanish on the stationary surface Rz, right? This precisely is our condition. Okay, so what we see that this transformation of gauge parameters, they do not affect transformation of our fields modular terms vanishing on the stationary surface. So if we have a solution to our equations of motion, and if we apply gauge transformation of the following type with parameter which is like pure gauge, which is generated by Z, then our solution is not affected by this transformation. That's why we have a name gauge for gauge symmetries. These are like gauge symmetries for gauge parameters, not for fields, but for gauge parameters. Of course, this philosophy can be iterated. We can speak about gauge for gauge symmetries, and then we are talking about higher stage reducible systems, and these systems, in fact, they are present in applications. Although it looks quite exotic, it's not so difficult to give an example. Maybe on the next page, let me give you an example of such a system. So suppose this is a two-form, the simplest two-form gauge theory. It's a gauge theory whose field is an antisymmetric tensor. So A equals to maybe half A mu nu dx nu. So it's a two-form. And gauge transformation is like this. Delta of A is the RAM differential on epsilon, where epsilon is now epsilon mu dx mu. It's a one form. And it's easy to see that if we consider the following transformation of epsilon, d on lambda, where now lambda is a zero form, because epsilon is a one form, then delta lambda, then what we have that delta lambda epsilon of A is 0, because thanks to d squared to 0. Of course, in a similar way, you can consider higher form gauge theories, which are going to be higher reducibility state, highest stage of reducibility gauge theories. So you see this is a characteristic feature in Lagrangian formalism. You have a transformation of gauge parameter which does not affect transformation of physical fields. Which means that there are redundancy in the description of our gauge generators. There are zero modes of our gauge generators, or in other words, we have reducibility relations between gauge generators. And in this case, the action is typically taken to be something like d for x, for instance, if in 4 dimension, f mu nu rho, something like 1/6. And f mu nu rho is a d mu a nu rho plus d nu a rho mu plus d rho a mu nu, right? So it's just a d of a in invariant notations. From this representation, it's obvious that our Lagrangian, our action is gauge invariant, right? Because f does not change under the gauge transformation, but still we are dealing with the theory with gauge for gauge symmetries, or with first stage reducible gauge theory. And let me get back to BV. So in this case, in general, we need to introduce GOST eta A. It's conjugate antifield eta star A. And now our BV action reads like this. It's S naught plus phi star I Ri alpha C alpha plus C star alpha Z alpha A eta A plus terms of high resolution degree. And resolution degree of eta is taken to be eta star, is taken to be 2. And GOST degree of eta is taken to be also 2. Okay, so it's very much in parallel with what we discussed in the Hamiltonian setup. So if you have next stage reducibility relations, you introduce new variables such that they incorporate these relations into the master action, so that master action indeed knows everything about our gauge theory. And this can be extended to higher stage reducible theories, but that's what we don't discuss explicitly. And finally, exercise about this, which is very simple, is find SBV for this 2 form. Because this theory is linear, everything is simple, everything stops at lowest degrees. Find SBV for 2 form theory. So you will have to introduce GOSTs associated to these parameters, and you will have to introduce like next generation of GOST associated to parameters for parameters. Okay, our time is over. So thank you very much. Please do some exercises on your own, because this is an important part of our exam or whatever. So for me, the rule is to, if a student wants to pass exam, she or he is supposed to solve a certain number of problems from different parts of the course, and to be able to demonstrate it to me. And then we can chat about theory, but practice is very important. So please don't ignore it. Please consider exercises which I give. Also, you can find plenty of exercises in my lecture notes, which I hope you have. I saw someone put it to the chat, and perhaps I need to send an updated version, it's minor update, some typos, some minor improvements, but still it's better to have one and the same for everybody, especially before exam, because then it's easy to refer to particular problems as problems in the lecture notes. Okay, very good. So see you next time, and our plan is to have it in 1 week according to the standard schedule.